that allow certain freedom in the choosing certain representations. And the other method was cheaper in the sense that it didn't have any parameters. It was exactly the minimum what you need to get it. Okay, so properties that are why mimetic differences are attractive. Because they have uniform accuracy. You can have uniform accuracy up to the boundary and near the boundary. So if you want second order, it goes all the way to the boundary. And there are many methods that cannot do that. Normally you have second order in the interior, first order on the boundary. Second thing, you don't use ghost cells at all. And you could have actually second, fourth, sixth, eight, the order you wish. But it's uniform. You can, if you don't want uniform order, you can do that too. And this is a particular characteristic because no other mimetic method has that problem. Also, we work with classical solutions. Probably some of you are familiar with the notion of weak solutions. When you have partial differential equations, normally the solution is weak, and then you have, and the weak solution is some sort. It doesn't satisfy the original equation, but satisfies the integration of that equation. And so this actually considers a classical solution, but that doesn't mean that if you have, for instance, a discontinuity in your initial data, the method cannot solve that well. So in general, what we prove, we assume smoothness of the solution. But if your data is not numerically, the method probably in many cases solve that. We cannot guarantee that it doesn't always, because we are assuming the theory that this is smooth. And also that it works in a structured grid. And what I mean for a structured grid, it will be curvilinear structured grid. So essentially, you have a box and you or a rectangle, and you can deform it smoothly. Smoothly up to a certain point. Okay, so these are essentially the conditions. Then let me talk about very roughly what it is. It's a method that is based on the language of vector calculus. So what are the important operations in vector calculus? These are the gradient, the divergence, the Laplacian, the curve. And so this method tried to discretize those operations. Okay? So it has another issue, another characteristic. This method actually works with a pair of grids, not only one. So if you have a segment, for instance, suppose your segment, your 1D domain is given by these two points in black, that's the extremes, then you can split into several, let's suppose, uniform cells, and these are the nodes of the cells, and then the reds are the centers of the cell. And for a reason that I will not explain because we are a little bit behind in time, this gradient operator takes data on the reds and computes on the black, on the blues, and on the blacks. And the divergence operator has the other thing. It will be, because really what happens is the gradient, you compute the gradient of a scalar field. And the scalar field lives on the red ones. And the divergence, you compute the divergence of a vector field, and the vector field will live on the blue ones. Okay? But again, we can talk about this with more detail. There is actually more involved than as simple as this. Okay, so the composition, when you define the Laplacian is the divergence of the gradient, and it's essentially doing this kind of composition. And these representations, when you discretize, the gradient and the divergence are differential operators. But if you're working in a discrete world, essentially it's a matrix that has this number of columns and that number of rows. It will compute using, somehow, it will compute over here the partial derivative of this point, somehow using this reference. Okay? And so we have XC, C stands for centers, XN nodes, and we have also interpolation operators. Sometimes your data is on the center, but you want those to be on the nodes, and so we have some interpolations of high order that are mimetic also. They are uniform, even up to the boundary. And then you move your data from centers to nodes and from nodes to centers. Okay, it's just a summary of this. So what I mean is this G, if you actually, let me see, suppose you have a scalar field, okay, that is defined on 0, 1, say this is 0, 1. This your function is a continuous function, but what you're doing is computing the partial derivative. Okay, that's perfect. When I write the gradient of f is that. But if I discretize, f becomes a vector. And so this is a matrix. And my matrix, applying that vector, give me a result that should be high order. Okay? So the way it operates, you take the discrete function, which is a projection of the continuous into the mesh, and then multiply by this g, so g times that vector, and it will give you another vector that are those the values of the partial of the gradient of those points, and similarly the other one. Okay, so as I said, these are things that matter, and we can prove that if you have the scalar field and compute the gradient, and you apply this discrete analog of the gradient to the projection of this function to the grid, the difference is of order h to the k. K is the order of accuracy that you want. And again, for the divergence, you have another operator we call D, for the curl, another that we call C, and for the Laplacian, another one that we call L. Okay, just so the error is in the order k. You can fix the order you wish. Okay, important things. So this method derives the whole thing, all these properties, from a goal that is trying to approximate the integration by parts formula. The integration by parts formula is given in this formula. So we have here, let's say, the gradient of f, and here the divergence of f. Okay? And so the idea is you have this identity, which is the integration by parts formula, and I would like to write that in terms of these operators. Okay, it turns out that this is impossible to do, to approximate with a high order accuracy if you are trying to approximate this integral with a high order, with a clean quadrature, with a standard quadrature. So you need some weights. Okay? And the idea is that you approximate this integral by this function. So this is the inner product of B with GF using weight P. Okay, so this integral becomes this plus some order, some error. And that means if you say that V is a vector of ones, actually it gives you a rule to approximate integrals. So this is extremely important. Why? Because anytime that you have the divergence, in this particular case, a gradient, you can approximate the integral of a gradient by this expression. Okay? And something similar happens to the divergence. You can approximate the integral of a divergence in this expression. So the trick, if I want to show conservation of things, of mass, energy, momentum, the idea is I have a PDE, and then I integrate. I do some certain algebra just to have everything in terms of divergence and gradients, and then integrate. And I convert those integrals into these products. And that actually, so turns a problem that is with integrals, it becomes a matricial. That you'll see that is what's going on. Okay, in addition to that, this P and Q that seems to be magic because what I have, I have an approximation for the gradient and for the divergence. Those approximations were G and D respectively. I need to find this P and Q, and actually there is a relation. If you have G, you can find P, and that is given by this equation. P and G are, and Q, sorry, P and G are diagonal matrices because these are quadrature weights. And so this is a diagonal, actually. When you multiply a diagonal by this, it will give you the components of this, and you have a linear equation to solve that. Okay. So, by definition, we have these properties from the in integration by path formulas. We have these other properties, and then we can prove from here all the identities of the vector calculus in the discrete form, and also that for systems of conservation laws, that this is a particular form of a PDE, we can prove that there is conservation of mass, momentum, and energy. Okay, so obviously that was 1D. What happened in the 3D case? In the 3D case, the version of the divergence in 3D we will use for that Kronecker product. And this is one divergence in 1D in the x direction, one version, 1D divergence in the y direction, and 1D divergence in the z direction. I don't want to enter into the details, but you can construct this just in terms of Kronecker products. I just remember the following. The only thing that I want you to remember is this thing has 3 parts. This actually is the derivative with respect to x. These are the derivative with respect to y, and these are the derivative with respect to z. Just remember that. And there are certain matrices that are showing up, but here essentially zeros and identities. But I don't plan to cover that. The same happened to, or something similar happened to Q. Q is the weight of the quadrature weight. We were talking about a quadrature weight in 1 dimension. If I want it in 3, it will have this form. And for the interpolators, also, I will need to interpolate because when I am in several dimensions, sometimes the points are in the middle faces, sometimes the points are in the middle of edges, and so I need to move things around. But the important thing is an interpolator operator, in this particular case from centers to faces, has a diagonal form. In 3D, has 3 components, in 2D, has 2 components, in 5D, has 5 components, and so on. Okay, so that's essentially, you have done a course in Mimetic methods already. The idea is, this is the system of conservation laws. This is a PDE. Okay, you have a certain variable u, the derivative of time, and then you have the divergence of certain field f equals to 0, and there is an initial condition, and also there are some boundary conditions. The domain in this particular case is a cube in d dimensions. Okay, and we have C conservation laws. That means we have C equations. So these are vectors. Okay, so we have C equations, and actually U depends on x and t, and x is in the space of d dimensions. Okay? So this is the equation. F has this form, and now I will do the proof. But don't worry, I don't plan to enter into details. It's very simple and very short. So if I write f in this way, I could write the previous equation in this way, and then if I try to, this is the continuous equation. I try to discretize this, the derivative of time will become this delta, and that expression becomes this, where the component of j are the d's that were on the diagonal, and the i's on the diagonal, and f are the components of f. And the last thing, having that equation, what I do is I pre-multiply by this quantity, h, a constant, which is the mesh size, a vector of ones, and the cube in the dimensions. And just because the product of these things can be approximated by integrals, I don't want to go into the algebra, but this is actually what happened. This approach approaches the integrals of that. Whenever you have one q, you can approximate the divergences. Okay, but again, it's just that this is just avoiding all the details. This is the proof of the mass conservation. Something similar happens to momentum, something similar happens to energy. And that's it. In C dimension, in C equations in D dimensions, or all of them. Okay, one example. This is a 2D Euler equation. This is the equation written in conservation form. Actually, this one has 4 components. We have the density, horizontal velocity, vertical velocity, and the total energy. And the field F has these two, has 4 components and is composed by 2 elements. By 2, we are in 2 dimensions. So C is 4 equations, and D is 2 dimensions. Okay. This is an example that I found in a book. We have these equations are close with the ideal gas law. Given by this, that relates the pressure with the density. And I choose it because we have the answer for that. I need a lot of parameters. So you have a family of possible solutions. And the domain is given by this. There are certain parameters. The initial position is given by that. The initial velocity is given by this. And we are using this. I told you that there was a CO ground method that was developed in 2003. It was the first one. Let's say the more compact version of that was the Corvino-Castillo, was from 2019, I think. Okay, we use that for all the space derivatives, and we use a leapfrog scheme for the time. And this is just snapshots of the solution of all variables at certain moment. And this is the one that matters. This is the conservation of the variables that are here. So you see, we have the conservation of the vertical velocity, or then we have the energy on top, and we have the density and the other, these are together, the density and the horizontal velocity. And we have another example. Again, this is a 1D Burgers equation. In this particular case, the initial condition has a discontinuity. So in theory, we shouldn't be able to use the method for doing this. But it actually captures perfectly well the evolution of this. This is a particular instance. And so you have the initial data is this. And then mimetic for order at certain point in time is doing this. So this is supposed to move that way. And there is a calculation here about the conservation of energy is compared to 4 different methods for discretizing in time and you not time, but time and space. And you compare, and this is the energy. The energy is supposed to keep constant, and you see that the mimetic for order does it, and the least Federici is kind of doing the same thing. Questions? That's it. Questions? Yes.
You showed some different time schemes and the energy loss there. Is there any work? Is it even possible to have a mimetic method in time?
Yes, actually, I have been working on that. And it turns out, so there are several possible avenues, but I took the most simple one, and I found that the family of BDF, the backward differentiation formulas, those, all of them supposed to be mimetic. And actually, if you take a look at what those are, they are up to 6 orders. They are stable. So that is something that we're trying to develop, but there are still other possibilities, and so correctly we are doing.
One comment. For example, if you are solving a problem that has a Hamiltonian structure, then you can use a symplectic time, and then you get energy conservation in time and space.
So I know that you like movies. I will try to show you one. It's interesting. This was done by one student here at the master program. So this is the Allen-Kahn equation. Let me probably do this. But let me actually show you another one that is really most interesting. This is a problem of wound healing, and that is using all this. Sorry, this is not. Oh, I see what I mean. Oh, this is actually a Navier-Stokes problem. So there is a channel from this fluid coming in this velocity in this direction, and there is a cylinder over here. Okay. So let me just show you how it develops. So the first graph is the horizontal component, the other one is the vertical component. Okay, so just to show a little bit, then let me actually show you the last example just to allow you to go. This is, sorry, let me stop this. So this is a wound that is closing. Hope I can make it larger. Let me go. This was done, as I said, when a student using Mimetics, and he did it in a period of 3 months. He actually read a paper, he found that, and actually this simulation is much richer than what the paper offers. Okay, guys, so that's it. It was just to share with you what we're doing, and it's a big effort trying to theoretical proofs of this. These methods actually have really nice properties, but we need to still show or demonstrate that that's the case.
Well, thank you.